Welcome, guys. Yeah, so keep talking about group theory. Yeah, so we already talked about the symmetry group. So before I start, let me just advertise a little bit. Yeah, so I will put my group theory lecture in. So we already talked about the permutation group, and yeah, so next we will talk about some advanced topic like I think like the accounting principles, and also talking about the direct products and the direct sum, and also like the semi-products and the solvable groups and the C-Lows theory. Yeah, so basically some so starting from now, our group theory will be much more difficult. Okay. Yeah, so hopefully I'm okay. Okay, so yeah, so this video we will talk about another counting ideas, counting formula. Okay, so yeah, so so let's quickly see the definition. So definition, so our G will be a default, by default is a group. Suppose you give me two elements A, B, and G, and I can define B say to be conjugate. So B say to be conjugate to A. So it means that there exists the C in the group G such that A C inverse. So B is the same as CAC inverse. This is called conjugate. Okay, so lemma. Okay, so I use a notation that A conjugate with B. Okay, so conjugate is an equivalence class in G. Okay, so proof. So first, we need to check that A is conjugate A as A, right? This is trivial by choosing C is identity. Okay, and we hope to prove that A is the same, A conjugate as B, then easy to see that B conjugate as A, right? The reason is that B is C, C inverse, so A will be C, B, C inverse, right? So A will be C inverse, B, C. So since C is so we are in a group, so obviously that C is in a group. C inverse is in a group. Okay, so the third is basically A conjugate to B, B conjugate to C, and A conjugate to C. Okay, so let me just maybe just use this. So A conjugate. So we want to prove this, right? This is simple, right? Because B is CA. There's a let's say called DAD inverse, and the B is conjugate to C, so C is EB E inverse, right? So combine these two, you get C equals to E DAD inverse C inverse, right? And you make this as another group element. So C is ED inverse, right? So C is conjugate to A. Okay, so this is the equivalent class. Okay, so from now I can define some notation. So let's see of A is called the equivalent class of A. Basically, it's all the element which conjugate to A. So all the element in the group conjugate to A. Okay, so this is conjugate class. Okay, so I denote notation the number of A's, the number of elements in CA is called CA. So up to now, so start from now that our group are all finite group element. Okay, a finite group. Okay, so obviously that since it's equivalent class, right? So G will be sum over A, CA. So which A is the different equivalent class, right? So yeah, so we have this formula. Okay. Okay, so let's talk about normalizers. Okay, so given element called normalizer of A, basically it's the all element belongs to G such that it commute with A. Okay. Yeah, so all the element in G such that it commute with A is called normalizer. Okay, so somehow I call it N of A. Okay, so lemma. So it should be very simple for you guys. So N is a subgroup of G. Okay, so in order to prove a subgroup, we prove identity. So identity is in it, right? And the conjugate should be okay. Sorry, the composition should be okay. How about next? How about the inverse? How about inverse? Okay, so let's see inverse, right? So inverse means that we need to prove that AB belongs to N of the band notation. So A tilde B tilde belongs to N of A. We need to prove that this belongs to N of A, right? But this is simple, right? Because we know that so A tilde B tilde times A, since this commute, right? So I can do it as this, right? And this also commutes, so I do this, right? So satisfies this, okay. And also A inverse, if A belongs to N of A, then obviously A inverse belongs to N of A, right? The reason is that if AX equals to AX, then obviously that you get A inverse X equals to, you get the X, base notation, so A tilde. Okay, maybe I use X, right? So I have this, and I take an inverse, so you get the A inverse X inverse equals X inverse A inverse, right? But you times X from this side, so you get inverse X equals to X inverse A inverse X, and you times X inverse this side, so you get X A inverse equals A inverse X. Okay, so A inverse belongs to normalizer of A. Okay, so this tell you that this NA is a subgroup. Okay, so since it's subgroup, we can talk about quotient, right? So N of A is a subgroup of G, so we can talk about coset. Okay, so now comes the important theorem. So theorem is that the CA, the number of the conjugate class, the number of element conjugate in equivalence in A is the same as the G divided by N of A. Okay, well basically it's the G divided the cosets, how many cosets it can form a series. So this is a theorem. CA, right? So it's all CA is all the element X belongs to group G such that it commute with A. Sorry, I'm stupid. So CA means that all the X inverse A inverse, right? S inverse A X belongs to group G. And also, I want to prove it's one-to-one corresponding to G quotient N of A, right? So N of A is subgroup, not necessarily normal. So I need to prove it's using the right coset. Okay, so actually this must be right coset. Okay. Okay, so so I start in prove this direction. So what means that if I given any X, Y belongs to the same coset, then I want to prove that they are in the same CA. So they are the same CA. Okay, so this proof is not difficult, right? So since in the right coset, so basically, I think I can write, let's say this is an AX, Y, and sorry, an AY, right? So this is the right coset. And yeah, so that means this, right? So that means I can write Y X inverse is just N, right? Which N is some number, some element in the NA, right? So Y is NX, right? So but from here, one can show that so Y inverse AX will be NX inverse a NX, right? But N belongs to N of A, right? So N commute with any element of N commute with A, so I can commute this becomes X inverse AX, right? Because A commute with N, right? So they belongs to the same class in the CA. Okay. Okay, so on the other hand, what, right? Suppose we have the, so this is 1, 1, 1, 1, right? So if they are in the same right cosets, they give the same CA, okay? So let's see, suppose they are in a different cosets. So suppose X and Y are different cosets, they belong to different cosets. And then G. And we want to claim that X inverse AX is what? Will definitely not the same as Y inverse AY. Okay. Okay, so this is easy to show. Okay, the reason is that suppose not. Suppose not. So suppose not means that we have this, right? So from this, one can easily see that if you I times, let's see. So I times y from left. So I got the y inverse a equals to a y x inverse, right? Which tell you that y x inverse become n of a, right? So that means they have the right concept. Okay, so which we prove that if they are different, then they must be different. The same, they must be the same. Okay, so let's give the map. Okay, so we can take our results finally become CA, the absolute value of C, the number of order, the number of element in the CA is called CA, is the same as the G divided by normalizer of G. Okay. And then we also have sum of CAA equals to G, right? So we got the A, G, and A. Okay, so this is our final result. This is the sort of counting principle. Okay, so this is the famous theorem we will keep using. Okay, so let's talk about applications. Okay, so this application is very not very difficult. Okay, so remember that we define center, right? So center of group G is all the element which looks as the same as identity. So all the group G, all the element in G such that they commute with all the element. Right, so this is the center. Okay, so and obviously that the center is a subgroup of G, normal subgroup of G, right? Okay, so there's a given simple lemma. Okay, so let's say, so what if A belongs to Z of G? Then what will happen, right? So the lemma I want to say that if A belongs to Z of G, which tell you that if only if N of A is G. So yeah, so Z of A, N of A is G, right? So this looks, so what do we mean? So remember what's N of A, right? N of A means that everything commute with A, right? So X, AX, right? So this still be right because A belongs to Z of G. That means every element commute with A. So which definitely show that N of A is G. If N of A is G means that everything in A commute with G. So A will be a center. So this is just the tautology. Okay. Okay. So so once we have this observation, okay. So let's talk about a real application. Okay. So this application is famous result. So let's go. So if your group is prime power, which is n is greater or equal to let's say 1, then your center of G cannot be trivial. Basically, your center of G cannot be only identity. That means everything there should be another element which commute with all the G. Okay. Okay, so proof using class equation, right? We start with G. So this G is basically all the CA, right? Okay, so I can separate into two, right? So for every A, there's only two cases, right? The first case is that it commute with everything which is in the center, right? So let's see. So let's write as this. Okay, so there are two cases. The first case is that A commute with everything. Also, basically A belongs to Z of G. And if A belongs to Z of G, right? Then N of A will be just the whole group, right? So this is means 1, okay? Plus A do not belongs to ZG. If A do not belong to ZG, right? Then this N of A is must be a subgroup of G, right? So this N of A must be some P to the N, let's say P to the MA, right? Which MA cannot be the same as N, right? Because if MA is the same as N, then N of A will be a whole group. Even though it's in the whole group, the A should be a Z. Okay, so this guy should be written as a G. P to the N minus MA, right? Which MA is greater or equal to 1. Okay, so write everything down. The first term is a number of elements in the center, right? So it's plus P, some element A such that MA greater or equal to 1, where P N minus MA. Sorry, MA cannot be the same as, so MA should be less than N, right? Okay, otherwise that the A will be a center. Okay, so you see this, this is P to N, right? So would you prove that, would you prove what? You prove that your center of G is equals to Pn minus this, right? Right, but the problem is that this is divisible by P. Because every element is divisible by P, right? Because MA is less than N, which means that center is divisible by P, right? So center cannot be trivial. Okay, so this is a proof. Okay, but what is these results will give? Okay, so 0 and 2. So this is also famous. If your group is prime power order, then your G must be abelian. Okay, by the previous lemma, we know that the Z cannot be trivial, right? So center cannot be trivial, but center is a subgroup of G, right? So there are only two cases. The first case is your center is just the prime, the power P, right? Or center is prime P squared. If your center is P squared, then sure Z is abelian, right? Sorry, G is abelian because everything common with everything, right? So Z is P squared. If Z is P, who tell you what? Who tell you that let's see, if Z is P, right? Then I can take element G belongs to G, which is not the same as Z, right? And I define another group called Z tilde such that Z and as G, right? And then forms another group. Okay. So we have ZG, which is also G. Right? But the problem is that this guy is just P, and this guy is P squared, right? So, and ZG is different from Z because G is not the same as G is not in the Z, right? So, which tell you that the only case, the possible case is that your ZG, this group will be exactly the same thing in G, right? Because okay, so let me explain what ZG means. Sorry, I'm stupid. So this should be written as ZG, but it is all the element commune with G. Okay, so let's ensure that we have ZG, Z, and the G. And this is P, right? This is P squared. Right? These are not the same, right? So the only case that ZG is P squared, right? But ZG is P squared means that everything commune with G, so G should be a center, right? But I take it that G is not a center, so this is contradiction. Okay, so that means this case cannot happen. So the only case is that this is P squared, G is abelian. Okay, so this is another theorem. Okay. Okay. And next time we talk about Cauchy theorem and also this about a symmetric group, the conjugate class in the symmetric group, and after that we talk about the Steele's theorem. Yeah, I think Steele's theorem is the most difficult theorem in the group theory. Okay, I mean at least for the undergrad elementary one. See you guys next videos.